Good morning, everybody. And today we are going to learn about the refrigeration system as a part of this fluid mechanics and HVAC lecture. So let's go on. So before I actually talk to the refrigeration cycles and those kind of things, so let me talk a little bit about the history of refrigeration cycle or refrigeration. So in basically I mentioned a few things in here in earlier stage or in earlier of the civilization, the Chinese actually used to store the wine in a normal ice or snow to keep it cold. And in ancient India or in ancient Egypt, actually people used to use a kind of a earthen jar to cool the liquids. So it's a simply still you can find this kind of jar, for example, this kind of jar to make it cool in the village area of an ancient Marin in India still now. And then laterly in 1834, Jacob Perkins, an American, actually developed this closed refrigeration system with the liquid expansion and liquid compression to produce the cooling. And then he used actually a kind of a ether as a refrigerant. And nowadays you have a different types of refrigerant. We'll talk about it laterly. And then he used a kind of a hand-operated compressor to make it run, and then used a condenser and evaporator to have a closed loop refrigeration cycle. So which actually nowadays is developed in a sense, but still we are still using the concept developed by the Jacob Perkins. And you know, there is a thousands of area of this kind of refrigeration application. So I just mentioned few in here. So there should be much more actually than the one I am mentioning in here. So first of all, we do use this kind of refrigeration system to have a like a comfort air conditioning system. So it could be in like hospitals, it could be in a residence, it could be like our university building, or even in our rooms during the summer times, in our offices and hotels everywhere. This is a kind of a mandatory use nowadays in everywhere in the world, even in Norway, you can say. So, and then there is in use of a medicine, manufacturing and preservation of medicines. I think that we have this COVID pandemic situation now, so I can make an example of COVID vaccine. For example, the Pfizer vaccine that we need to keep it cold around the minus 70, 80 degrees centigrade. So that's the one of the another application. So we could use this kind of refrigeration cycle. We could use a refrigeration system to make it cool all the medicines for the manufacturing or for the preservation. And storage is a huge application, because you know, there's all the grocery shops and all the big market, they used to use a kind of storage and transportation of food. For example, when you nowadays it's very easy to get a product from US to here or here to Asia, for example. This is due to this nice cooling concept for their transportation and also the storage. So you can use all as you usually use at your home, also for the fruit, for the vegetables, for the meat. So everything is there. And manufacturing of ice is a kind of another uses of this refrigeration cycle. You need a lot of ices actually in a hard environment. For example, in Middle East, in Norway also, in everywhere you need an ice, and then you need to use this kind of refrigeration cycle. And processing of textile printing work and photographic materials that you need to actually use this kind of cooling system. And also cooling the concrete for a dam. When you produce a dam for electricity production, then you need to actually cool it down the dam to make it contain in a very wet environment. and also production of the rocket fuels, computer functioning, because nowadays is very good use. I could say this one, the computer functioning. We are like, we have a lot of data. So all the data center that they used to use a kind of a cooling system. So nowadays is a really huge use, and a huge is a multi-million-dollar market, I should say, in the computer functioning and our data center cooling. And now I can talk a little bit about the basic of the refrigeration cycle. So you can see the basic is to remove the heat from one specific space and make it cool, so that that could be utilized as a cooling point or cooling environment. And then you have when the refrigerant absorbs the unwanted heat, that rise the refrigerant temperature. That means it reached the saturation temperature. When it reached the saturation temperature, then it actually changes the phase from the liquid to gas. It means it evaporates, and this is actually important. So in a refrigeration cycle, I might say, so I will come back to this diagram laterally, just to know you said when it actually reaches the saturation temperature, it actually changes the phase from the liquid to gas, and go through actually the compressor, and then you have a condenser. The condenser, it again changes the phase from the gas to liquid after it condensate, and then it actually comes to the expansion valve again. And then when it actually changes the phase from the gas to liquid, then it's called the latent heat of this refrigerant. Okay, so this is the main basic of this refrigeration cycle, or how it works. And then the cycle is based on the physical principles, and that would be extract the heat from the surrounding area, and it expand or boil to a gas. So when it actually, for example, you know, I don't know you have seen or not in a refrigerator at your home. So they have their own refrigerant. Actually, it has their own boiling point, for example, or saturation temperature when it reaches. So, for example, if I use one refrigerant, it's called R134A. So it has a specific saturation temperature. So when it reaches the temperature, it starts to evaporate. That means it starts to change the phase from liquid to gas. Then it actually it happens like a cycle. And to accomplish this, the refrigerant is pumped through a closed loop pipe system. So as I mentioned, you have a closed loop pipe system, as Jacob was actually presented in 1834. There's a closed loop system. Yes, and now let me explain how the refrigerant works. In this actually class, I hope almost all of you know, but those who don't know, maybe today you know how it works. So you know the refrigeration cycle that I'm showing in here right now. So it's a kind of a reverse Carnot cycle. We already studied the Carnot cycle in your thermodynamic courses. Now this is a kind of reverse Carnot cycle. So what are you doing at like a refrigerator at your home? Like we have a low temperature reservoir, as you can see in here. Then you have a high temperature reservoir in here. So the basic point is actually like it collects the heat from the environment, from the surrounding, from here, as you can see. Then it starts actually to evaporate, as I mentioned, with the temperature. So it actually heat is absorbed from the surrounding, as you can see, and it is done by some work input, like electric input in here. You are providing the electricity in here, for example, CT to this compressor. You consider this is a kind of compressor, and then it actually helps you to transfer this one from the low temperature reservoir to high temperature reservoir. Normally in the Carnot cycle, and it actually goes like high temperature reservoir to the low temperature reservoir. That's why they don't need a kind of extra work for this cycle. But in here, you are actually providing the low temperature reservoir to high temperature reservoir. That's why you need a kind of work input. That means the electricity in this case. And then when it actually removes the heat from the surrounding, for example, this is the surrounding that we are talking. Okay, so when you actually remove the heat from this surrounding, it makes you cool down this temperature in a specific temperature. For example, in our normal refrigerator, it's 4 degrees centigrade or 5 degrees centigrade that you're talking. And then it is actually maintaining this temperature, this surrounding, by using this principle. So then we can say how the refrigeration or refrigerator at your home is working now. I hope you can explain to your younger brother or friend now. Yes, and as you know, actually the main thing of this refrigeration cycle is like to know about the COP, or like what is the COP of this refrigeration cycle. So in that case, like you can say for the refrigerator, the COP, that means the coefficient of performance. It should be like how did the desired output. That means this is the amount of work that you are providing to the refrigerator. So you can say this QL divided by the required input. How much input you are providing? That means W net. Okay. And this is for the refrigerator, and also for the heat pump. I'm taking this one because they are working at a kind of same principle. So it's basically for the refrigerator, we are using this space to cool down. For example, this space to cool down, but in a heat pump, we are actually producing heat to warm up this house, for example. So that's the difference. But so in that case, COP, that means the coefficient of performance for the heat pump, it would be the QH divided by the W net in this case. So that's the difference. So in the desired output for the refrigerators in here is a QL, however, for the heat pump, it would be the QS in here. So what is the main purpose? The main purpose of the refrigerator is to remove the heat, which is called also the cooling load. That means in this case, if I ask you to calculate what is the cooling load, then you have to find the QL in this case, and to make it cool in here. And what is the purpose of the heat pump? To heat pump is the heat transfer, the transfer the heat to a high temperature media, which is known as a desired output, or the heating load. In this case, this is the cooling load for the refrigerator. So this is the basic difference between the what is the principle of the heat pump, what is the principle of the refrigerator. It's just the how we utilize the heat or heat transfer. And as I mentioned in one of the earlier stage or earlier slide, that actually this refrigeration cycle is a kind of reverse Carnot cycle. So as you can see in the reverse or in the Carnot cycle, you use a kind of a turbine in here. So the turbine is actually replaced by the expansion valve. This is the only change in the refrigeration cycle and the Carnot cycle. And the working way, the working principle is like is actually first it came to the compressor when you are providing some electric input in here, W. So it actually goes to the refrigerant. If I talk about the refrigerant, it goes to here to there, and then there to here to there, and here to there. So this is the kind of a cycle, continuous closed loop cycle, Carnot cycle in a reverse. Okay. So and then if I actually draw the TS diagram, I'll talk a little bit details after this in one of the slides today. But just to give you how it works for the TS diagram for this reverse Carnot cycle, it's like in the 1, 2. That means this is the compressor work. This is like a condenser work. This is like expansion valve work. This is the evaporator work. And then this is how much amount of heat that you are removing from one specific space or on a surrounding to make that cool that space. Okay, and okay, now a little bit talk about the types of refrigeration cycle. So basically, we have two types refrigeration system. One is known as a vapor compressor refrigeration system, and another one is called the vapor absorption refrigeration system. Today, we mostly talk about the vapor compression refrigeration system. Let's talk. This is very nice to explain. So I already talked a little bit about this process. As you can see in this figure, this is like a compressor and the compressor, and this is a condenser. So this is the main four unit. If I ask anyone, like, what is the basic unit of a vapor compression refrigeration cycle? So you can say that there is a four unit. So one is like the compressor, and another is like a condenser, and then another was like expansion valve, and the other one is like evaporator. So these are the four units that we use to have a vapor compression refrigeration cycle. And now we will talk about first about the ideal vapor compression cycle, and then afterwards we will talk about the actual vapor compression refrigeration cycle. So in this case, as you can see, first, as I mentioned, there is a refrigerant. For example, in this case, as an example, we are taking refrigerant R134A. So according to the different application, you can choose different types of refrigerant. I will talk about the refrigerant in the next lecture. I'll not talk more details about the refrigerant. It's actually dependent on what is the application, what is the purpose, and also what is the regulation in a specific country, and what is the impact on environmental impact and global impact. So those are the things that we consider to select a refrigerant. So in this case, as you can see, first, when it comes to this stage, the evaporator, after the evaporator, you'd get saturated or superheated vapor. And now, saturated and superheated vapor, we already talked about this in a thermodynamics. What is a saturated vapor? What is the superheated vapor? It reaches after the evaporator, you may have like 100% of vapor or gas, or a mixture of both. So it comes to the compressor. And what is the purpose of a compressor? The main purpose of the compressor is to compress. That means by utilizing the heat, by utilizing the electricity, you could actually compress the superheated or saturated vapor. And the basic way is to from the low pressure to it actually give you the high pressure. So if I say this is like a low pressure vapor mixture, which is goes when it passes to the compressor, you generate the high pressure vapor or vapor mixture. Okay, so and then you would get both the vapor, high pressure vapor in this case. I mean, I'm talking about the refrigerant R134A. Then it actually reached point 2, from 1 to 2. So okay, at 1 you can say the low pressure vapor, it actually compressed in the compressor, and it reached a high pressure vapor at point 2. So what did happen? So it had actually like a high pressure vapor, it reached at point 2, and then you have a heat exchanger, which is known as a condenser for this case. What this condenser is doing is actually removing heat. As you can see, the Q out is removing some heat from that high pressure vapor to make it cool down. That means when it actually passes through this heat exchanger or condenser, it actually removes some heat from this refrigerant, and then it will produce, as you can see, the liquid. That means the high pressure vapor condensed to high pressure liquid. At point 3, you could get the high pressure liquid. So at point 3, you are getting the high pressure liquid, and then it actually passes through the expansion valve. And what is the main purpose of the expansion valve? It expand. So when you expand refrigerant, so or any kind of liquid, it actually changes the phase from the high pressure to the low pressure. That means after the expansion valve in here, you may reach in at the point phase liquid vapor mixture of low pressure. I could say the low pressure two-phase liquid vapor mixture. And then when it reached point 4 and it passed to the evaporator, that means in the evaporator it actually received the heat from the surrounding, or get the heat from the surrounding, and then it actually evaporates this phase liquid vapor mixture. It will be evaporate to the saturated or superheated vapor, you can see. So that means by getting that surrounding temperature, for example, if you use this refrigerant, it start with evaporate or saturation temperature for this evaporator for this refrigerant. You may consider as an example is a 5 degrees centigrade, for example. So when it comes to the 5 degrees centigrade, it receives some heat from the surrounding. For example, at home you have a surrounding temperature of 20 degrees centigrade, for example. So it receives the heat from the surrounding and it starts to evaporate to change the low pressure two-phase liquid vapor mixture to saturated low pressure vapor completely. So, and it's repeating again and again, again and again. So if I can show you, so I can show you this. I can draw a line in here. So this line I am drawing because to show you this is a kind of high pressure zone to talk about. This is the high pressure zone, and this is a low pressure zone. Same thing you can see in here. This is a high pressure zone. This is a low pressure zone. Okay, this is the main principle of a vapor compression refrigeration cycle. And now, if I just talk a little bit again about the what is actually happening from point 1 to 2, you can say this is a kind of isentropic expansion. Okay, entropy will be remain same, and that's why it's called the isentropic compression, as you can see. And then 2 to 3 is a constant pressure. So at point and point 3, you can say the high pressure. It's not changing the pressure, high pressure to high pressure. So that's why you can say this term as a constant pressure heat rejection in the condenser. It rejects heat, the Q out amount of heat you are rejecting to the environment. And then 3 to 4 is known as a throttling in an expansion valve. So what is that? You can see it's actually changing the high pressure to the low pressure again. And then again at point 4 and point 1, we can say this is a constant pressure heat addition. It's adding some heat from the surrounding, as you can see the Q in here. Okay, so I hope at least that you may actually explain about this vapor compression refrigeration cycle, and it's really interesting. And now in this case we talked about the ideal case. So we are saying, okay, there is no changes of entropy and there is no losses to the pipe, because you know this is the pipe. If you don't have an additional insulator in those pipes, as I show you in here, so which means you can actually lose a lot of heat to the environment. So in an actual case, that would be you will face this kind of heat losses. So then you could say that one as an actual case. But in this case, we are saying this ideal vapor compression cycle because we haven't considered any kind of losses in this process. And now, as you know, this is some mathematical equation that you might use to evaluate the performance of a evaporator. So if I ask you, like, what is the refrigeration capacity? So you have to remember, this is like how much the amount of heat actually receive from the surrounding in a world. Okay, so that could be actually you will get it by using H1 and H4. And how do you get this H1 and H4? I'll come back to this point in the next slide, or the slide after two. And in this case, just remember what is the term. You can say this Q in or Q dot is known as a refrigeration capacity. So in some cases, you could use the ton of refrigerant. Okay, so then you have to actually divide the amount that you got it in kilojoule, divided with the 210 kilojoule per minute. Then you would get it in a ton of refrigerant. In most of the case, if you go to the shop, and you ask, okay, I have this size of houses, and then they will say, okay, you need 4 ton of refrigerant capacity to cool down your house. So this is the way of expression, ton of refrigerant. So you have to remember that point. And then what is the compressor work? As you know, I was denoted in the previous slide, and okay, a point one is to say again, this is like a compressor. So this is a point one in here, and then this is a point two in here, if you remember. Then it connected to the condenser, then it connected to the expansion valve, then it connected to the evaporator. Okay, so just to remind you, this point 1 to 2. So if you know what is the enthalpy of point H1 and what is the enthalpy of point 2 H2, then you could say what is the compressor work that you might need for this running this refrigeration cycle. And similarly, if I told you this is a condenser, and if this is a 0.2, this is a 0.3 in this case, and this is 0.4 in this case. So you can say, if you know what is the enthalpy for 0.2 and what is the enthalpy for 0.3, so you may know what is the condenser work. Or and similarly, if you know what is the H3 is equal to H4, then that means you may know what is the expansion valve work in here. And now I was talking in the previous two slide about the H1, H2, H3, H4. And now I would actually show you how you could calculate this H1, H2, H3, and H4 in a pH diagram. So this one is known as a pH diagram of refrigerant. So in this case, we are considering again this R1, 3, 4A refrigerant. Okay, so for that refrigerant, I would give you, actually you need a 2 temperature or pressure. So you need a temperature for the condenser, you need a temperature for the evaporator. So if I just tell you what is the pressure at the evaporator, and then for example, in this case, I draw a line for 1 bar. I gave you that temperature is a 1 bar, so pressure is a 1 bar, and the temperature of a refrigerator and the evaporator is minus 20 degrees centigrade. So I will follow this line, as you can see in here, until this is the temperature line, as you can, the red color line in here. Okay, this is the temperature line. This is the temperature line. By the way, I took this this figure from Coolpack. It's a kind of a software that we used to use to draw this kind of pH diagram, to know about the refrigeration properties and those kind of things. So it's known as a Coolpack. If I just write in here, Coolpack. So let's come back in here. So this is the pH diagram, and then you can say, if I just show you 1 bar and minus 20 degrees centigrade, then I need to reach that this point in here. Okay, reach this this point, and then as you can see, this is the entropy line, and this is the enthalpy. As they mentioned, you can see this is the enthalpy, and this is the pressure, and these are the temperature, 10, 20, 30. These are the temperatures. Similarly, the temperature is also mentioning in here as a red color line in this graph. This 10, 0, minus 10, minus 20, minus 30, minus 40. Okay, and then this entropy will be remain same. Then you, as I mentioned, so this is a 0.1, and then you can draw a line as the entropy remains same. So you can say it could reach at 10 bar, this in here, so that it remains same entropy, same entropy, same entropy, same entropy, and it will reach until in here. Okay, so this is the entropy line. So you have to make balance in that point. So this is the 0.2. Okay, then you can draw a line to, this is like a condenser work. So as I mentioned, the condenser pressure or temperature is like a 10 bar and 40 degrees centigrade. Okay, so this is the condenser pressure is 10 bar and the temperature is 40 degree centigrade. Then you will reach this point in here, which is known as a point 0.3. And then you just directly draw, if you draw the ideal vapor compression cycle, you just draw a line, straight line, because the enthalpy for the is remaining same. That means H3 is equal to H4. Then you have to draw a line, straight line until in here. Okay, so it's sorry, my drawing is, it should be a straight line in here, and then you will reach the 0.4 in here, which is, and then you can draw a line in between these two at 1 bar. So that means at 1 bar you are reaching from 4 to 1. Again, for your understanding, I'm talking this 1 to 2 is known as a compressor work. Okay, and then this 2 to 3, if I just line that through, this one is known as a condenser work. And then this is for the expansion valve, and this 4 to 1 is known as a evaporation work, evaporation. Okay, so by knowing these things, actually you can easily calculate what is the like a H1. For example, for this case, the H1 would be like around 390, for example, 90 kilojoule per kg. Okay, kilojoule per kg. And for this point too, you could reach this point in here, which is around 445 kilojoule per kg. So this is for H2, right? And the H3 and H4, which is around, you can say 260. So H3 is equal to H4, which is around 260 kilojoule per kg. And then if I ask you what is the cooling capacity for this case, so you can directly actually find the cooling capacity, or QL is equal to this H1 minus H4. So you can calculate what will be the QL. If I ask you what is the condenser work, then you can define H2 minus H3. Then you define what would be the condenser work. So this is how you could calculate the refrigeration calculation. And if I ask you what is the COP for this case, in the COP for the refrigerator, in this case, it would be like this evaporation work or cooling capacity. This means the QL divided by how much work. That means if you know what is the H2 and H1, that means you can tell how much work that you might need to run this refrigeration cycle. Then in this case, it is the W net in this case. Then this QL is equal to, you may say, this H1 minus H2, sorry, H4, and then you can say the W net is equal to H2 minus H1. Then you can define what is the coefficient of performance for the refrigeration cycle. I hope you get an idea about the refrigeration cycle and pH diagram now. So if you have any question, just ask me afterward, or just send me an email. And now I will just talk about how we differ the actual vapor compression cycle. So, okay, before I go to the next slide, so this is the pH diagram. Just to show you how the pH diagram would work for the refrigeration cycle. So if you just consider this is like a temperature in this case, and this is the like a entropy S, then this is like how we do work normally. Okay, so it's I'm talking about the refrigerant R1, 2, 3, 4. So in this case, it would be like you can say 1 point in here, 0.2 it would be in here, and then you'd get 0.3 in here, and 0.4 should be in here. So this is the pH diagram. Now let's go back to the next slide. What is the difference between this ideal vapor compression cycle and normal vapor compression cycle? So let me show something in here. So, as you can see, as I mentioned you, you know the temperature. I mentioned you the temperature for the condenser, or the pressure for the evaporator was like a 1 bar and minus 20 degrees centigrade. So you got the 0.1 in here. And now, I told you actually there should be some losses in the compressor. There should be some losses to the pipe. And then if there's no loss, you can reach the 0.2S. So 2S is for the like ideal case, but in reality, you can see you may reach this 0.2 in here. So because this is the like temperature for the condenser or condensing temperature, but in reality it reached this temperature in here. So in reality, the compressor might use more work to produce higher temperature than this temperature, pH, the temperature for the warm region, pH again. So this the reason why you reach point here, and also you reach the temperature. For example, in the previous example for the pH diagram, I told you it's like a 40 degrees centigrade for the condensate temperature. But in here, let's say this is a 40 degrees centigrade in here, but this is a for around 45 degrees centigrade. So in reality, due to the higher work of compressor, it may reach 45 degrees centigrade. So that's why you may get this line in here. So that's why I am talking the actual vapor compression cycle due to some losses to the compressor, due to some losses to the pipe. And then as you that's what I told you. Okay, let me show you like this. So refrigeration temperature in evaporator is less than, for example, this case it reaches higher in the condenser, and also similar due to the same losses, actually it may reach lower temperature due to the expansion valve losses, due to the losses in the expansion valve in a pipe. It may reach much lower temperature than the cold region. In the cold region, I mentioned to you in minus 1 bar and 1 bar in the previous example, 1 bar and minus 20 degrees centigrade. But in this case, if we just consider this is a minus 20 degrees centigrade, this is might be around minus 30, for example, degrees centigrade. So it should work at this point according to the ideal vapor refrigeration cycle, but in reality, in actually, it reached to this point, the temperature is minus 30. So you can see, okay. And then similarly, the condenser temperature is greater than the TH. That's why I already talked to you. And then this is a kind of reversible process. So in an ideal cases, we talked about reversible. So wherever it reached, it came back in the same way. So this is a reversible impact or reversible heat transfer for the ideal vapor compression cycle. But in the actual vapor compression cycle, we may get the irreversible heat transfer. So that's why we are not actually following the same curve again and again. It might differ 1 degree, 2 degree less, or 1 degree more for the condensing temperature, 1 degree or 2 degree or 10 degree less for the condenser temperature. So that's why this is known as a irreversible heat transfer. And it has a negative impact on the COP. So that's why If I can mention you for the vapor, ideal vapor compression cycle, if COP is one cycle is like around 4.5, but for the actual vapor compression cycle, it may decrease due to the high work needed for the compressor due to the temperature changes in the condenser and evaporator. It may reduce the COP, which is actually a negative impact of the COP. Okay. So, and it's decrease. So that's why you have to remember that for the fuel cycle, the COP will be actually decrease gradually. And this is due to these changes. Actually, I already talked. Just to kind of repeat the changes, as you know, the changes on the temperature, like it changed from this phase to here, and it also reached a higher temperature from, as I mentioned in the previous slide, 40 to 45, and in here is a -20 to -30, for example. So due to these changes, it has an impact. And also, as you can see, if you would like to work from 2S, you may need to work less than the 0.2. So if the compressor need to reach 0.2, it might need more electricity to run in the compressor. So that's why you need, that means that's why NW net, it will be increased. So if the net W net is increased, for example, then W net is increased, so that means COP will be decreased, because the correlation of COP is equal to QL divided by W net. So if this is increased, the COP will be decreased. So that's the correlation. Yeah. And that's all for today's lecture. Today, actually, let me remind you what we have learned. So basically, at first, I started the history of the refrigeration cycle, how in ancient India or ancient Egypt, ancient China was invented some cooling process, and then we talked about the Jacob Franklin, who invented this refrigeration cycle back in 1834. We know about how he invented and how he worked with the ether as a refrigerant. And then we talked about different application. As I mentioned, thousands of applications of this refrigeration cycle. And then we talked about some basic things about this refrigeration basics, 4 components, about the compressor, about the condenser, about the expansion valve, about the evaporator. And then we talked about the basic principle of vapor compression cycle. And we talked about the COP. We talked about how normal refrigerator work. And finally, we talked about 2 types of refrigeration cycle system. One is a vapor compression cycle, and another is a vapor absorption cycle. We talked today about the vapor compression cycle. We talked how the vapor compression cycle works. We talked a little bit details about how to calculate the impact of a evaporator, that means the cooling load, how to calculate the heating load, how to calculate the compressor work. We saw how the pH diagram looks like, and we saw actually like how the pH diagram looks like. We saw how the actual vapor compression cycle work, and how in actual vapor compression cycle COP is reduced, those kind of things. Thanks for the lecture. Hope it will be helpful for your understanding. Thanks a lot.